这样有录音？
有，开始录音。
Okay. Hello everyone, I'm the TA for this course, and now I'm going to introduce the term project. And here are the references for the term project, and I will, in the following slides, I will focus on the first approach called Ultron. And here is an overview of today's slide. And I will start by defining the problem, then explain how Ultron can be applied. After that, I will go over the dataset and show some example code. At the end, I will talk about what you will need to do for the term project. And how to do document retrieval with a large language model. In traditional information retrieval, we usually build an index of the document. So given a query, we search through this index and return the most relevant document. When using an LLM for retrieval, we can reformulate the problem as a sequence-to-sequence test. So the input is a text query and the output is a document ID. And the LLM can generate several document ID, for example, like this integer sequence. These integers represent the received document. So you can think of the training process as encoding the encoding the entire corpus into the LLM's parameters. Then, during inference, the model generates document representation that are most relevant to the given query. And this is how Ultron works when doing document retrieval. And on the right-hand side is an overview of the Ultron approach. And it uses an encoder-decoder architecture for document retrieval. First, the text query is encoded into dense vector. Then the decoder generates the corresponding doc ID. And the key point in generative document retrieval is how to represent documents. In general, designing better document representation usually leads to higher recall. And in Ultron, it uses product quantization code as document representation and performs constraint bin search to generate a ranking list. So this is how Ultron works when doing document retrieval. And in our term project, we don't use text as the data type. Instead, we use vector as our data type. So the problem will become vector retrieval, and the task becomes vector to vec ID. And as you can see, all the text, document, and doc ID are replaced by vector and vec ID. So to make this change, all you need to do is skip the encoder part and feed your vector directly to decoder. So you can see on the right hand side is the overview of the original Ultron approach. And when the query is already a vector, we can skip the encoder part and let decoder generate the vector ID autorecursively using constraint bin search. And here we have a tree structure called a prefix tree. It is used to constrain the search result and make sure that the generated vector representation actually exists in the database. At this point, you may wonder how can we perform autoregressive generation if the model's output is an integer, but the input is a vector. In our example code, we use the centroid produced by PQ and project this centroid into a higher dimension to align with the input dimension. So each vec ID corresponds to a centroid, and we project that centroid to the same input ID, to the same input dimension. And this way, the model can perform autoregressive generation properly. And this is how Ultron works when the problem becomes vector retrieval. And in our term project, we use SIFT1M as our data set. And the training set is called the database, and it contains 1 million vectors. Each vector has 128 dimensions, and each vector has 100 neighbors. The test set contains 10,000 queries. But in order to control the difficulty, we build our own data set. So it has 2 versions. The first one is the small version. It contains 10,000 vectors in the training set, and 1,000 in the test set. And the other one is the medium version. It contains 100,000 vectors in the training set and 10,000 in the test set. And I will explain how to use these 2 data sets at the end. Okay. In our example code, we use T5 as the model architecture because in Ultron source code, it also uses T5. And as we mentioned earlier, we don't need the encoder part, so we only train the decoder. And on the right-hand side is the model configuration. You can check the document provided by Hugging Face through the link below and modify the parameters as needed. And note that these 2 parameters are fixed. The first one is vocab size. Vocab size is the output dimension of the LM head, and it should be the number of your vector representation. And the second one is D model. D model is the dimension of the hidden state, and it should be the same as the input dimension, so which is 128. Now I will briefly go over our example code. Here is the file structure, and basically you will be working with utils.py and dataset.py and train.py. The first one is util.py, and you can modify all the parameters in the getArgs function, such as model configuration we talk here, and maybe your training epochs or learning rate. You can modify the parameters in this function. And the second one is dataset.py, and we perform PQ in this file. So if you want to use another type of vector representation, you can modify this part of code. And the last one is train.py. In this file, you may want to design your own loss function. So you can find a function called compute loss and modify this function. In our example code, we only implement the indexing loss, but you can also add a retrieval loss to possibly achieve better recall, or even redesign your own loss function here. Okay. And this is the README. First, you need to set up the environment, and you have to check your CUDA version by you can use this. You can use in this comment to check your CUDA version. If your CUDA version is not 12.9, please change the CUDA version and to fit your machine. And after your environment is ready, then you have to reproduce the recode here to make sure your code runs properly. And note that the recode may be slightly different, so it's okay as long as the result is close. And second note is that the test set is not the real test set. It is only used to check whether your code works correctly. Okay, and this table shows the baseline performance on the two test sets, and these test sets are the real ones. So you can refer to this recall to estimate how much recall your model can achieve on the real test set. And this is the baseline training setting for the true version. Okay, so in our term project, the first step is to reproduce the baseline result using the test set without noise. And after that, you can start modifying your training settings or model configuration or vector representation, or redesign your loss function to improve your model. And the goal is to finish this table. You need to fill in all the missing value for each row. The first row is your reproduced recall, and the second row is your methods recall. And note that the medium version is optional. So if your machine can run this version, it's okay to only provide the recall for the small version. But if you complete medium version, you will get extra point. Okay, so this is our term project, and I will put the example code on equals 2, so you can download it. And the real test set will be released later. So now you can evaluate your model on training set or construct your own evaluation set. So this is our term project. Have any question?
Okay, so thank you, Bill's presentation. And remember that our deadline is the deadline is 16 weeks. Okay, our last week in this semester, our 16 week, you have to give 10 to 15 minutes to present to report your result, and give a presentation to make a slide to briefly introduce how you do it and what's the problem you encountered and how do you manage your modification to do your project and show your result and share with your thoughts with us. Okay, so everyone, you have prepared 10 to 15 minutes slide presentation for your term project at our next week. Okay, for any questions for code problem, please consult our assistant. So our lab number is 305. Okay, welcome to talk with our assistant, and if you want to take a break, a tea break, and you can go. Please welcome to go to our lab.